Hi, hope everyone's sufficiently refueled with coffee. Thank you for inviting me here, and thanks for all the talks. It's been a really interesting conference for me. I'm talking about the back action in the circular motion Unruh effect, the exact thing that was just talked about by my supervisor, Yorma, which is very convenient for me. To be clear, this is back action on the field. That term is sometimes used to refer to gravitational effects that come from the interaction. This is looking only at the field instead of looking at the detector. So, some background, the Unruh effect, as I hope you're all very aware of by now, is accelerating observers measuring a thermal bath, whereas an inertial observer would measure a vacuum. Any questions are referring to Yorma's presentation, which focuses on the detector itself. But the question I'm asking is flipping that on its head on the other side of the coin. What does the field look like? And what insights can that provide to us about how the system evolves and what that could mean about the energy distributions and all kinds of other interesting things? Also worth noting is that there are talks about this potentially being measurable in the same lab, in Silka's lab that Yorma was talking about, but that's stuff that's probably too early to even mention in a talk as a side note. So sorry, Yorma. Standard frame Hamiltonian, this is in coordinate time, so lab frame, because it's more convenient for the math. There are factors of gamma to work in proper time. And each of these terms will be useful right now, even though you're very familiar with it from the previous talks. So lambda is the coupling constant, and we expand in terms of it, we get the lowest order of it. It's very important. The chi is the switching function, which determines when the interaction is switched on, when it's switched off. Very common, this is set to just be 1, so there's always interaction. As we'll see later, we can't have such a convenient choice in this case. Mu is the monopole moment operator of the detector. This is very often what we're interested in, what the detector is doing, but instead I'm looking at phi, the field. And worth noting, this field, in my case, is massless and scalar, and we're working in 2+1 Minkowski spacetime. Very similar to Yorma's talk, surprisingly. This circular motion is parameterized in this fairly standard way. This is not very revolutionary as far as the trajectory goes. It's very common, it's very well studied in the literature, and it's currently what's being simulated in the gravity laboratory just in the office next to mine. Constant acceleration, you get constant temperature, but you don't need an infinitely sized lab, which, as Yorma said, is hard to get funding for these days, and it's well studied in comparison to linear acceleration, as we all know by now. To get information out of the field, we can't just ask the field itself, we ask questions about the field, and we do that via observables that tell us about certain dynamics. These observables, in this case, are calculated to linear order in the time evolution operator. This is fairly important. This is neglecting some terms in the final observable, which correspond to the detector being excited and de-excited. So the question we're asking here is specifically, if the detector is excited, what do we see? There could be some influence from excitation and de-excitation that we couldn't just sequester away in higher order terms. It might be useful. But for now, we're just looking at the question of there is excitation, what's going to happen? Some common examples of observables that people tend to look at. We have our phi squared, simple to calculate and very common throughout all the literature. This is calculated largely for comparison purposes. There's also this rho. Rho is a thing that Will Unruh is actually quite interested in, and it represents the Klein-Gordon norm and can then be used to calculate the number density of the field as a distribution. I'm not doing either of them today. I'm doing the energy density, the energy momentum tensor, but the T00 term. So the distribution of energy within the field after the interaction. There is, of course, the question of switching. As I alluded to earlier, Constant switching is very convenient, very nice. The maths is very simple. But the questions that we ask are not, because there is a non-physical behavior that arises from the fact that it's a weak measurement, and therefore by Aronov's work long ago and his interpretations of quantum mechanics, we get non-physical behavior from the future. So effectively, if there is interaction in the future, we will see effects from that reaction in the past. And we get this causality breaking because we can't know the future. So instead, we have to find some switching function which is defined only for positive times. So, no, sorry, positive times. Switching function which is compact and has some maximum time beyond which there is no interaction. First thing we considered was cos to the 4 interaction, which is very nice. It looks kind of like that. It's this little bump, goes in and up and down again. And key thing is 0 for all times greater than 1. So we can look at times greater than, oh, okay, this has a is 1. So for all times greater than a, we have 0 interaction. We can probe that. There are no nasty questions about causality. It is smooth to a third derivative. It is a good approximation of a Gaussian switching function, which is by far the most common that you see in nearly all the literature with particle detectors. As long as you look within the region that it's interacting. Obviously, if it's 0, it's not as good a comparison. But where it's close to the 4, it's a very good comparison, and we can investigate the field. But we can do one better than this, because we can extend this backwards and have cos to the 4 switch off and cos to the 4 switch on, and some duration in the middle. So this setup, we have this parameter b, and b defines when the detector is switched on. And the smoothness is still defined by a. So we can take b to be any reasonable number, and then we take a width a around, width of 2a around that. We switch on in that time, we switch off at a duration 2a centered on 0. So we have this gradual switch on, gradual switch off, and this controllable interaction duration. We still have no causality breaking. We don't know about the future, which is very handy. And what I'm about to do is say that we can easily, not easily, but we can, while being careful, take the limit as this b goes towards infinity. So we effectively have this tangent-looking graph where we're interacting for an infinite amount of time, and then we slowly switch off, and then we aren't interacting. And then we can ask the question, what is the state of the field after there has been this infinite duration interaction? And hopefully with this, we can extract maximal information about how the interaction behaves, how the field is affected. We're going to look at plots now. The plots are a lot to digest, but they are quite fun to look at. Just some notes, we have A is set to 1, so the switch off and switch off is relatively sharp, and the speed of the detector undergoing circular motion is 0.7 times the speed of light. So it's traveling quite fast. And all of our numerics are dimensionless with respect to the frequency of the circular motion. And that allows for much more convenient things. You have, so the radius of the motion then becomes r equals 0.7. The math is much easier. What we get is these spirals, which is good, it's what we expect. The detector has been for an infinite amount of time going in a circle in the middle, that around, in the middle, and it's been emitting this long spiral, and then this plot is taken at the very instant that the interaction has been switched off. So there is no interaction at this point. We take a snapshot, a space-like hypersurface of the field, and we say what it looks like. So this is the distribution of energy within the field after the interaction. We can expand that. We can ask at different energy gaps of the detector. So as I mentioned before, this Unruh detector has a controllable gap parameter that we can change. It can be positive, which corresponds to the detector needs to be excited to change state. It can be negative, which corresponds to the detector falls and is de-excited to get to that state. And as we change it, we see a drastic difference in how the field reacts. So if there is a large excitation gap, so the detector really needs a lot of force to get it up and over this, force is the wrong word maybe, energy, to get it up and beyond this, there is actually very little of the spiral still visible. It's a very short duration and very, there's less energy. It's a much lower likelihood of an interaction, therefore there is much less of an interaction with the field. So we see this slight thing here, and then as we increase the energy gap towards zero, more of a spiral emerges. And then here we have de-excitation. In de-excitation, we expect more of an interaction, and we see more of an interaction. So this spiral behavior continues, and it's very well behaved and very nice. And it moves. I'm quite proud of this. And you can see the emitted mode being emitted outwards in a spiral direction. You can also see the mouse being very confused with what's going on. It's as excited as I am. And for excitation, there's this small, much more kind of localized particle, much less prominent interaction, and it's emitted outwards into the field. Then the more of a de-excitation you have, the easier the interaction goes and the more extended it is throughout the space-time.
What breaks spherical symmetry?
Say again, where'd that come from?
Breaks spherical symmetry.
Spherical symmetry.
I mean
the circular symmetry. So the detector path itself is not circularly symmetric. There is this time. It's a stationary path, but the interaction is not.
It emits mostly in a certain region of the circle. Okay, so you are saying that it emits.
The most prominent area here is the area where the detector was most recently. So the fall off of the dissipation of the energy is less.
I see. So in the last ones, it emits only parts of the circle, right?
So this spiral exists, it's very, very faint. This spiral still exists for these, but it falls off so quickly, all we can see is where the field has most recently interacted with it.
Okay. Thanks.
And that is this little bit here. So the spiral still, it's this very, very faint spiral that still goes outwards here, but there's such quick fall off because the interaction is so faint.
Okay, thank you.
I'm going to show you a new plot now. This plot comes with a caveat. And that's that there is not sufficient spatial sampling and there is some sawtooth-like effects. They are not physical, they're entirely numeric. I apologize. Longer plots take days to make. So this is in 3 dimensions, and you can see, as I was talking about before, even with the excitation, the spiral is still there. It's just much smaller. These are 3-dimensional equivalent plots. So, to summarize, assuming everyone's done staring at the slightly trippy and enjoyable animations, there is an underrepresented and important question about what's happening to the field as everyone else is looking at the detector. And we look, for the sake of comparison and for easy visualization, 2+1 circular motion, in the hopes that maybe this will be comparable to some kind of experiments at some point. There is talk about what observables might be most akin to the surface of superfluids in the analog system. Very interesting conversations. If the detector needs to be excited, so it has this positive energy gap, we see a much weaker interaction and it decays much faster, which is interesting, maybe to be expected, but interesting nonetheless. And there is still future work to be needed. There is a question of whether it's possible to do the calculation non-conditionally, so whether it's possible to do a full calculation without assuming the detector has changed state. But I'll hope to know whether it's possible soon. And again, the comparisons to the experimental regimes are ongoing. Lots of good references here. I'll refer to them if you have any questions. Thank you very much for your time.
Thank you. Are there any questions? We have time for a couple.
So do I see correctly that of course your Unruh detector sort of takes energy out of the field in a sense? So this your field will have a negative energy density at some point, right? Or
not that I know of. So the detector is constantly putting energy into the field.
Oh yeah, of course. So
it's
it's
undergoing circuit. The energy is not conserved in this system. There is something constantly pushing the detector in a circle.
Yeah,
so it's in a way constantly putting energy into the field, and it has this conditional little jump that it can take.
But you're not seeing any violations of energy conditions in this process, or
not that I've seen. No.
Thank you.
Okay, we have one question here. Rick?
So when you plotted the energy density and very nice plots.
Leave it here. This is my plot.
Yeah. So in the case of positive energy gaps, which means that the detector starts in the ground state effectively, right? And it has it has no energy to emit, right? Then in the end you have to release, like you have to switch off the interaction. And then your interaction becomes time dependent, which means that the full Hamiltonian becomes time dependent. And then you will have a lack of conservation of energy due to this external energy that's being embedded into the system, right? That's the way that I see these waves leaving. But now, following up on the question from I don't know who asked, but so these plots, what are you plotting exactly? Is it the phi squared? Is it
this is T00.
This is the T00, and you don't see any negative energies. You don't see any negative energies at all.
No.
Like that's the okay. Like that this plot goes to 0, but it doesn't get negative at all. So okay. It's the same question. I'm just like trying to understand the physical side of it. Okay. Thanks. That's good.
There's another question there.
Hi, really nice plot. I really like this.
Thank you.
Just wanted to ask if I have a question and a comment afterwards. Just want to ask if anything interesting is happening before the switch off.
That is an interesting question. Unfortunately, it's not a question that can be asked because of most interesting questions can't be asked. It's very unfortunate. It is because of this double spiral behavior that we see. So this measurement of the field is a weak measurement. The measurements of the detector that most people do are exact measurements. Because of that, and because of the stuff that I can't explain here, but is explained very well in my first reference in Aronov's paper about two-time measurements, the weak measurement undergoing the interaction while there is still a strong measurement happening will see the future. And seeing the future is not a thing that we want to do in physics because that's scary. So we don't do that.
Right.
The construction doesn't work if the interaction is still going on. The questions about the field produce non-physical results.
And maybe the comment now, I just wanted to point out that it was Unruh who first proposed this detector experiment, and it's only fitting that Unruh is the one to propose again that we shift the focus to the field.
So the field focus is not new. This, where is it? Here it is. Bill and Wold's paper from 1984 does a similar thing, but with linear acceleration. It's an adaptation of that to circular motion.
Unfortunately,